Good morning, and thank you for joining us. I'm very happy to welcome today's colloquium speaker, Professor Anima Anandkumar, who's the Bren Professor of Computing and Mathematical Sciences at Caltech and Senior Director of AI Research at NVIDIA. Professor Anandkumar's research interests include the algorithmic foundations of artificial intelligence and its application in accelerating research in scientific domains ranging from autonomous drone flight to weather forecasting and computational fluid dynamics to quantum chemistry and drug design. She is best known for her work on tensor methods for latent variable models, tensor networks, and neural operators. Professor Anandkumar earned her PhD in electrical and computer engineering from Cornell University and did her postdoctoral research at MIT. She then joined the University of California, Irvine as an assistant professor in 2010 and was a principal scientist at Amazon Web Services from 2016 to 2018. She joined NVIDIA as a director of AI research and Caltech as Bren Professor in 2018. She is the recipient of several awards for her work, including the IEEE Fellowship, the Alpha P. Sloan Fellowship, the NSF Career Award, and faculty fellowships from Microsoft, Google, Facebook, and Adobe, and is part of the World Economic Forum's expert network. Today, she will be telling us about her work on accelerating science's neural operators for learning between function spaces. Welcome to IAIFI.
Thanks a lot, Matt. Thank you, Marissa, for organizing all this, and it's a pleasure to be here. Yeah, so today I'll tell you how neural operator is a framework that provides a foundation for learning between function spaces. Right? So operators map between function spaces, whereas if you think of a function that maps between finite dimensions or fixed dimensions. So how do we go from standard neural networks that learn functions that live in finite dimensions to a new framework, neural operators that can learn operators that map between function spaces? And what are the principles and how does it do better than standard neural? And we'll see why that is so essential for accelerating many of the scientific simulations, especially, for instance, those driven by partial differential equations. So if you have a family of parametric PDEs, you have a solution operator for that. And by learning the operator, we can then solve for any new initial conditions or boundary conditions, for instance, and do that very fast, much faster than what numerical solvers are able. And so we'll see how all that unfolds. Indeed, in a way, we are severely limited by computation in so many of our scientific simulations, right? So one example is climate simulations. For instance, my colleague Capio Schneider at Caltech, who is part of the Anima initiative, we also have MIT researchers be part of that. What he estimates is you need about 100 billion times more computing capabilities than what we have today, than even the most powerful supercomputers we have today, to be able to remove some of the biggest sources of uncertainty in our climate models. And so this cannot be achieved by just the use of accelerated computing like GPUs or scaling up and out on supercomputers with very fast interconnects. All those will help us accelerate simulation, but you need on top machine learning to take a big leap and see any hope of making these kind of hard problems tractable. And same with quantum chemistry. So if you think about like simulating quantum chemistry, that's also hugely expensive. And so what in this slide, I want to quickly just drive home the point again on climate simulations as an example of where we are today versus where we want to be, right? So ultimately, we want to resolve these low-lying clouds called the stratocumulus clouds that currently, if you do this from a bottom-up approach using partial differential equations, they're extremely expensive. And these are turbulent systems, so you cannot afford to do it at a coarser scale with the current numerical solvers. And so that's the computational bottleneck. And so how do we overcome that with machine learning? And so just as to kind of make that, like we are soon going to be approaching with numerical solvers the ability to compute at 1 kilometer spatial resolution planet-wide and 1 minute resolution temporally. But we really ideally want to be at 1 meter resolution. And maybe even further if we want to go to microphysics. So these are highly multi-scale systems, right? That's what I want you to take away from this. Current numerical solvers have no option but to get to a really fine grain. And that there's no way to directly resolve the computational constraints if you're forced to work on fine grain. So the hope is machine learning instead can learn features and do the computation in a different space. And by that feature transformation, maybe you can make your computations much faster and you're not limited to computing at the time. But the question is then how do we have good generalization with machine learning if you're learning such transformations? And as I mentioned, another example of such computationally bounded problems, or rather computationally limited problems, are those in quantum chemistry, like the Schrodinger's equation, for instance, requires about more than the age of the universe for just computing on 100 electrons. Right? So if you try to do any of this through force, it's really, we have no hope. We do have approximations like DFT, but even those are very expensive, and so you cannot go beyond a few hundred atoms, even on the world's most powerful supercomputers. So the question is, what can machine learning do to these really challenging problems? And so this is where we'll look at the framework of neural operators, and in particular, how Fourier neural operators are efficient instantiations of neural operators for solving many of these problems. Yeah, so the first question is, why not just standard neural networks? Right? We have convolutional neural networks, we have transformers, so why not just use them? So if you try to use them in scientific domains, the main limitation is that these networks generalize only on the same level. The whole framework of a neural network is you have training and test data, ideally of the same distribution at the same resolution, then you know your model will generalize well to test data. But if you train it in one resolution and ask it to generalize to a different resolution, or query at a point that is not part of the same grid, in fact, many of the networks don't even allow you to query outside the grid of the grid, right? And even if you do, the generalization may not be very good. But on the other hand, when you have numerical solvers for different simulations, such as PDEs, you want the flexibility to run on any kind of thing. Right? So you want to be able to query at any point in the domain. And I don't know what apparently with the sound is the problem. So do you think this will solve the problem? Is this better for people online? Okay. So just take that off. Yeah. Okay, I'll stick here. So yeah, the idea is we want to keep the flexibility of numerical solvers in having the ability to train on different resolutions of data or different grids of data, right? Being able to query at any point after training and without having to retrain. Of course, you could do a hacky approach of train in one resolution. If you now want to generalize on a different resolution, you retrain. One is it's hacky. The other is, by doing this, you're not necessarily learning the underlying continuous operator, right? So ultimately, you want the mapping between these two function spaces in domains like partial differential equations. And we don't get that by just learning on one fixed resolution or one fixed grid. And so that's the main limitation of neural networks, or one of the limitations of neural networks that we want to overcome by framing it as neural operators. And so the way we want a neural operator, what are some wish lists we want, right? So as I said, we want this notion of discretization invariance. That doesn't necessarily mean you get the same answer at every discretization. That is too stringent to satisfy. But what you want is some kind of a consistency, meaning if first of all, you should be able to query at any point in the domain. And that rules out, for instance, convolutional neural networks, because there the grid is fixed. You cannot query outside of it unless you do something like interpolation on top of it, right? So you cannot directly use that. And so that's the first requirement. The second requirement is, as you keep refining your mesh or grid, in the limit, it should converge. So a limit should exist, right? So the idea is, in this example here, you've trained your neural operator, let's say a model with some fixed parameter weights. You've trained it, and then you give this as different inputs. So you can give this mesh as an input to the neural operator. You can now refine the mesh and keep giving these as inputs successively at inference time after you train. And what you want the solution or the output of the trained model to be is to converge to the limit. And so what this means is also it rules out, for instance, doing simple interpolation, right? Though that doesn't necessarily have such a limit. And so that's what we need, something more than just doing standard interpolation on top of current neural networks. So instead, we'll see that the neural operators will have this guarantee that you can query at any point. You can also be ensured a limit exists as you refine the grid after having this neural operator be trained, or after you have this and you use it at inference time. And so what is the way we build the neural operator framework? So we said current neural networks are not enough. And we said we require this discretization invariance in our neural operators. So how do we go about building this? Of course, we always want to start with a simple case, right? So the simple case is one of a linear operator. For instance, think of a linear partial differential equation. If you recall your PDE 101, right, the solution has the form of an integral linear operator. So you can write this down in the form of an integration, which in a way is intuitive, right? The inverse of differentiation should be integration. And if it's linear partial differential equation, even this inverse should be linear, and that would have this form. So we know that this is the form of the solution. As an example, like say heat diffusion. So if you have uniform heat diffusion, you can even get the kernel in closed form, right? So in some special cases, you can even analytically write down the kernel. But in general, this kernel would be dependent on initial conditions, and if it's different in different places, right? It's it could also be in general not uniform everywhere in space, but you can it would still, any linear partial differential equation will have this form of integration. So because you have this integral form, we know that this outputs functions. I mean, you can always now query at any point in the domain, and this is by definition discretization invariant. Of course, if we did this integration exactly, so that's. But this is standard linear partial differential equation solving, right? So this is how we obtain solutions, and this the Green's function formulation. So what we want to do now is conceptually think of neural operators as compositions of such linear integral operators. But we want to compose it with nonlinearity in between, and that'll give it an expressive framework so that you can now learn any general operator. Apologies, I should be more careful. So that's how we came up with neural operator in its most general form, right? So what you want is a block, could be a set of layers here that will effectively be computing an integral linear operator. And then we'll compose it with nonlinearity, anything standard, ReLU, GeLU. Sometimes you want to avoid the ReLU because you want differentiation and you want higher order derivatives. But other than that, it can, any such well-behaved nonlinearity will do. And with that, what we can prove is this will be a universal approximator for any continuous operator. So the same way standard neural networks are universal approximator for any continuous function. If we had a framework that can compute integral linear operators and we compose that with nonlinearity, we get a universality result, and that we in fact prove that in our papers. And that's also because it's having the outputs as functions, it's by nature discretization invariant. Right, so this is like a formulation, and now we can ask what kind of practical architectures would approximate the integral linear operators efficiently, right? So that's the next step. But any questions so far? Again, I want this to be interactive, so feel free to interrupt me, and even online if there are questions.
The function inside is that special, or is that the matter what kind of integration?
So we will be learning those kernel, right? So that's the idea. So if you say you somehow estimate a kernel, and then on top of it, you can do the integration, or you can directly do the integration, right? So I mean, depending on the operator you want to approximate, that function can be anything general. Of course, if the function is smoothness, the operator has other properties, you can also further impose additional regularity on the kernel as well. So that's the general framework. Yeah. Yeah.
Are you still not limited by mathematician-wise?
No, because this is just integration on the entire domain, right? There is right now no discretization. But when you're training this, you can give an input that is discretized version of your continuous domain. So you can train it in various ways. But at the end of the day, once you've trained it, if it's still performing the integration or an approximation of the integration on the domain, it is approximating the operator itself, and not just one discrete grid of it, if that makes sense. Yeah. And that's why we're kind of starting from the foundation itself to say we should have this block approximate an integral linear operator, and not just a discretized version of it. And so end to end, we keep it as operator approximations, and that's why we can come up with the universality. We can also come up with finite approximation bounds for specific problem classes, like say fluid dynamics, the Navier-Stokes family of equations. So depending on the Reynolds number and other properties, we can also say what should be the size of the parameter, right? And for specific architectures like Fourier neural operator. And I'll come into those instantiations. But right now, the general framework is we have a block that computes integral linear operator, and with nonlinear compositions of this, end to end, we can come up with an approximation of any operator of interest. For instance, it can be the solution operator of any family of PDEs. Yeah, and this is kind of like driving home the point that I was making earlier, that if you just took like convolutional neural networks, for instance, right, it doesn't satisfy many of the properties we want in scientific domains. So you cannot have your input be at any point. So the query is output. I mean, in the case of, let's say, partial differential equations, you have the input at a point, you also typically query at the same point, but in more general cases, they could be different. And this is not true because convolutional neural networks run on a fixed grid. And obviously, because you can't query it everywhere, it cannot be universal approximators for operators. And so even if you did interpolation, you may not get this universal approximation. And so that's why, and deep nets are another framework. I won't get into that here, but neural operators are the only ones that can guarantee you both discretization invariance as well as the universal approximation.
Can you go back one second?
Yeah. Yeah.
So if I use a map from the linear operator as a map from function to function, v of y is the input function, right, and the whole integral as a function of x is the output.
Yeah. Thank you. Sorry. Yeah, I wasn't very explicit about that. Yeah, exactly. So you take any function here into the block. Here it's v is the function, and then you integrate it with the kernel, and the output of the block is that resulting function. And so as you see here, the input and output are both functions rather than fixed dimensional vectors or fixed dimensional objects. Yeah, so I haven't still told you what is an architecture that solves it, right? Like it's still like a wish list, because we're saying if you had an architecture that could compute this or approximate this integral linear operators, then we can have universal approximation. Is there further clarification? Good. Okay, because this is important. Once we, this is really the main point of the talk, right? And then, but you'll see, I think, once I show you the example of what we do with Fourier neural operator as an efficient way to realize this integral linear operators. So we'll make a further special case. So instead of taking all general kernels, we'll say, let's make them translation invariant, because convolution is. And indeed, this is a, you're making it a more special case, but it turns out you can still keep all the nice properties. And it becomes easier to compute this. Because once you make this as convolution, so you want to learn a kernel that does a convolution operator, then we can solve it through Fourier domain. And so I want to point out the difference here, right? So we are now asking for convolution over a continuous domain. So we're integrating over a domain, as opposed to standard convolutional neural networks that are on a fixed grid and that are also local. So you just have these local filters in a standard convolutional neural network. But with a convolutional operator, this can in general be global. So you can have this kernel be non-zero everywhere in the domain, right? Whereas in a standard CNN, you have just strict cutoff, and it's only local. And the other is it's not discretized, right? What you want ultimately is the approximation of this continuous convolution.
Sorry,
yeah.
Do you assume it's translation of invariance?
Yeah.
Yeah, because k is a function of x minus y. So right. Do you assume that it's translation invariant?
Right. Right. But in many cases that is okay. Like that's because so you'll see in the next slide why that's helpful, right? Because once we assume this, then we can transform it to the Fourier domain. So this is signal processing 101, if you recall, that convolution in the standard domain becomes multiplication in the Fourier domain. And so this becomes tractable now. So we can do this efficiently. And so what we're saying is instead of trying to learn the kernel and then integrating over it, you can directly learn the Fourier transform of the kernel and just multiply it with the Fourier transform of the input, right? And if you want, you can take the inverse Fourier transform and transform it back to the domain. I mean, this is a simple fact. But with that, what we can do is our layer now becomes very simple in computing an approximation to the linear integral operator. So we are doing the Fourier transform, learning the weights. So I'll just call this matrix R, which is the Fourier transform of the kernel, and multiplying with this weights in the Fourier domain and doing the inverse Fourier transform. So you don't have to first learn the kernel, then approximate it. In fact, we do have methods to also do that through graph neural networks and multi-grid graph neural networks to directly approximate the integral. But those tend to be computationally very expensive in higher dimensions and with more discrete, like finer discretizations. So much more efficient method is to do it through the Fourier transform. And so that's the architecture, right? It's very simple, but also efficient. And the idea of like how you can think of this as discretization invariant is you can, the fast Fourier transform is on one fixed grid, but you can keep changing the grid, right? So you can just do fast Fourier transform on different grids. And so that's why it's discretization invariant. You can keep changing it to any grid, and you can also query at any point by just doing the DFT instead of FFT. It's more expensive, but you can compute Fourier transform at any point in the domain in principle. And so that's how you get the discretization invariant and at the same time an efficient algorithm. Yeah, so that's the architecture, right? So you now have this operation in the Fourier domain, you learn the weights. We also do a bit of regularization, meaning we only pick the low frequency modes and we zero out with threshold and don't retain the high frequency modes. And this helps better in generalization in our empirical analysis. And the reason is because we have this nonlinearity, you can afford to do away with many of the high frequencies. I mean, if you only had this and it was a linear operation, of course, you have to keep all the frequency content, right? Otherwise, you don't get good approximation. But because we are doing this over many layers with nonlinearity, you can do this regularization and get good generalization. Because sometimes these high frequency modes here tend to be noisy, and they tend to be learning spurious correlations. So it helps as a regularization, and at the same time, it retains all the nice properties that we want in being a neural operator. And another detail is also you can have like a skip connection that does pointwise transform, like say this weights, take every point and learn a transformation, and in this case, a linear transformation. And so, for instance, Fourier transform is very good at capturing periodic functions very well, right? You can do Fourier continuation and also capture non-periodic functions. But having the additional flexibility of also a skip connection helps you learn better in many of our experiments. Some additional details, but those don't, right? Like they're still under the framework of discretization invariance. And so you can see that here in action as a simple example where we have the Navier-Stokes equation. You train it only using coarse resolution data. So I think 64 by 64 spatial grid. And without any retraining, it can also generalize now to a higher resolution and give you fairly accurate solutions. And so the idea is you don't have to keep retraining for every resolution. You train it once, and then you can do inference at any grid or any resolution, even change the grid. For instance, we have extensions of this to also irregular grids, and we can have this nice generalization. Yeah. Yeah, sorry, yes, one is exact, the other is the approximation. But we have all the right quantitative results in the paper. This is just to kind of show a quick visualization of what it's able to recover. Yeah.
Can you say any complete detail how you parameterize these functions?
No, that's exactly this. So we parameterize it by learning the weights in the frequency domain. Yeah, so it's very simple. Yeah, so the idea is it's simple, it's fast, but also very effective. And so I think that's the point I want to drive home.
Is there any universality result for only these convolution operators?
Yes, so you can, in fact, there's an extensive set of results where you can also get finite approximation bounds. For instance, for Navier-Stokes, you can say how many modes you want this to be, depending on, say, the Reynolds number or other smoothness properties. And also for, one of the recent papers, Siddharth Mishra and Samuel Lanther, who's now at Caltech, they show that you can also handle operators with discontinuities like shocks. So you can also get approximation bounds for those class of operators as well. Great. So, and recall, like, so even though we made a special case, right? So here, yes, we did say, it's translation invariant, but we are composing these with nonlinearity. So you can still get universality. But making this assumptions allows us to go to the Fourier domain, and it's much more efficient to compute. Yeah, so so we have this nice discretization invariant learning with Fourier neural operators. As a next step, what we are also investigating is kind of diving deeper into some of the optimization challenges, right? So, for instance, compared to standard deep learning, there's a lot more flexibility we can have here. Because we are querying the solvers, we can say, at what resolution should I be training these models, right? So the intuition is if you train it at a very coarse resolution, you can't possibly approximate the operator very well, right? Sure, it will work on any discretization, but you don't get a good approximation. But on the other hand, getting data at very fine resolution from simulators is also expensive. And so one approach, what we did was to do incremental learning. So as a next step, in recent project, what we are asking is here you can gradually learn with a bigger model as well as with higher resolution data. So you first give it just coarse resolution data and it learns the coarse level features. And over time, you can expand the model. And by expanding the model, I mean, you can retain more modes, for instance, here, right? You can weaken the regularization and you can gradually learn. And this helps in generalization. And it's also helping you with training costs. So far I've been emphasizing the inference cost and that's the running cost, right? That's what matters the most because we'll train it once, we'll keep running it, we'll keep querying, especially I'll show you examples of inverse problems, uncertainty quantification. Those require many, many runs from the operator, right, over many instances. That's the main cost, but we are also studying how you can improve training costs by doing this kind of incremental learning and also have a good understanding how the optimization landscape is better behaved by doing this kind of incremental training. Because there's a range of work in deep learning looking at the implicit regularization of stochastic gradient descent and having this kind of incremental trajectories, we can characterize them much better for these Fourier neural operators, because first of all, we can do that on parametric classes where we understand the smoothness and other properties and the scale separations, for instance. And also we can look at how well the learning progresses by controlling the resolution of training data in a very systematic manner. Yeah, and so that's more recent work that we are working on, where we can also nicely understand the optimization landscapes of these Fourier neural operators. So let me now, kind of also add a bit about what we can do by incorporating all the domain knowledge, right? Like so far, everything I said is purely data-driven. You don't even need to give me any physics. I'll show you some of the empirical works we're doing with weather forecasting, looking at experimental data of fluid dynamics. So using no equations, you can learn this, and the learning is effective. But in many cases, we don't have enough data, right? And in some cases, no data at all, because it's so expensive to run the simulator. Our moonshots are like the climate simulations or quantum chemistry I showed you, right? One day we hope to do that. And to do that, we cannot ignore the physics. We have to incorporate the physics. And so that's a natural extension of the neural operator, where the idea is you can now impose any kind of equation law. So you have a partial differential equation, you can just penalize if the equation is not satisfied. But one additional detail that makes this efficient is that you can compute gradients as well, and other derivatives very efficiently through Fourier transform. So if you recall, Fourier transform, the derivatives are also, right, like simple multiplications in the Fourier domain. So that makes it very cheap, and you can get exact gradients. Some the previous frameworks like PIN, the physics-informed neural networks, and others sometimes do like numerical approximation of gradients because they're cheaper. But here you can also get exact gradients very accurately, which is an additional benefit of using Fourier neural operators. And you can do the chain rule and other things, right? So you can do this end-to-end efficiently and also get exact gradients. And so you can also take this further, because so far what I talked about was operator learning. So you have a whole set of instances. So, you, for instance, give me now partial differential equation examples with different initial conditions and what the solutions are. So I'm doing supervised learning over many instances from the PDE family, and I learned the solution operator. But you can also further fine-tune it at test time, and now I want to solve for a very specific initial condition. If I have the partial differential equation, I can check if the solution of my pre-trained operator, what I've currently trained, is it good enough or not? And I can further fine-tune on that specific instance, right? Which is natural. If I want the error to be better than what my trained neural operator is, I can fine-tune it. So the physics-informed neural networks were only doing this. So what's been proposed, the PIN or physics-informed neural networks, they only take a single instance and from scratch try to find the solution. And that tends to be very hard in the optimization landscape. So that's why they cannot, most of the time, do any dynamics or any hard optimization problems for PDEs. But in our framework, our operator learning gets you almost all the way, but it may not get you the same accuracy as a solver, right? So if you want to go to really low errors, you want to then additionally fine-tune, and then you get best of both the worlds. So, you get fast learning with operator-based learning. And then on the same model, you can further fine-tune. You don't need to have another model. You just take your model, fine-tune on the instances you want. And you can also do transfer learning. It doesn't even have to be fine-tuning on the same operator as you trained. It can be on a distributional shift version. For instance, we can pre-train the operator on Reynolds number 100, right? So you can have a whole bunch of instances from a simulator at Reynolds number 100, but you want to go up to like a different Reynolds number at test time and fine-tune it. So if you directly do it without PDE loss, it's very hard to see how the two are related. You can even see that visually. The dynamics look very different. But on the other hand, if you have PDE laws here. So you have the physics-informed framework while training the operator for Reynolds number 100. It much more easily transfers to Reynolds number 500 because the equation has similar structure even though the Reynolds number is different. And so that's the other benefit of this framework. You learn the operator, but also incorporate the physics constraints. You can much more easily transfer it to related families of equations with, say, different, in this example, Reynolds numbers.
Sorry,
yeah.
So can you do a meta learning version of this thing?
Yeah.
Like you input the Rayleigh
Absolutely.
number and
yeah, and we are doing that now. Okay. And that's a natural one, right? And the idea is by using the physics-informed version, that meta learning or transfer learning becomes a lot nicer because then you're explicitly saying what is the relationship between these different, parameterizations. Yeah, yeah.
So what you do in practice, if you go one slide back, please.
Oh, yeah.
What you do in practice is for one PDE, and you give the examples are different boundary and boundary condition. Also,
initial or boundary or whatever changes you want to make, right? Yeah.
And then the test set is one different initial and boundary condition. And on that one, you can find it. Okay, thank you.
Yeah, because you can just run your pre-trained operator and see what the error is. But now you can check, right? Because you know the equation. You can see how far you're from satisfying that equation. And if you're not happy, you can further fine-tune and make it more refined. Yeah.
So in practice, how do you encode your training outputs? Do you have to have a functional representation of it, or do you just have various discretizations of it? Or
yeah, discretization is fine. There could be other parameterizations too, right? This framework allows for any kind of representation of the inputs, but the simplest is discretization. Okay. And as I mentioned in the incremental learning work, what we're investigating is, can you gradually increase the resolution of training data? And the intuition is, you may not need to go all the way to very fine resolutions, right? Because at some point there is good enough information to approximate the operator. And so this way you also save on getting data from simulators, which can be very expensive with numerical solvers. Yeah, there's a question there. Yeah.
Yeah, I was wondering, how do you define the time window that you're doing your integration on, right? Because find the discretization can vary, but the time window also is a free parameter, right?
Yeah, that's a good question. So, for the examples I'll show you, or the ones I showed, the time, the total time is fixed, right? And you can do different discretizations of that, and it'll work. But if you want to go to arbitrarily long trajectories, we have another work that I'm not talking about it here, that'll appear at NeurIPS in a month or so, where what we do is, for especially chaotic systems, there is no hope of estimating the actual trajectory, right? Predicting it well, but we can compute the invariant measure. So we can approximate the attractors, and we can simulate it over very long periods. We can do very turbulent systems, say like Reynolds number 5,000 or even higher. But in that framework, what we do is not try to estimate the trajectory very long, right? So we only do a short-term evolution learning, and then we can compose it. But the one thing we have to be careful is it doesn't blow up. So we look at dissipative systems. We always regularize and keep it dissipative. And so you can get both approximation as well as the ability to simulate these chaotic systems. Yeah. But that kind of, it's true also with so many physical systems. Let's say, at some, from weather, you essentially go to climate, right? So the idea is climate is all about the chaotics. You cannot, I cannot say what exactly will be the climate 20 years from now, right? But I can give you the statistics of it. But weather over the next 2 weeks, I can tell you with some accuracy. And so in a way, like, as long as there is that predictability, you can, have it be trained, or you can use the PD losses and try to accurately predict it. But at some point when it's diverging, you shouldn't be training your models, any model. And in fact, a lot of research in deep learning on recurrent neural networks or LSTMs having exploding or vanishing gradients is exactly that problem, right? So you try to learn it over very long time intervals. That learning is not possible. So it just diverges, and you cannot have learning. And that's a good question. Like, if I just learn on the short term, can I just directly extend it to also getting the invariant measure? And what we've shown is the answer is yes. You can do that as long as you keep in mind to make it dissipative. Of course, not all systems are dissipative. Then how do I ensure it's well behaved? That's an open question. Hope that answers you. Yeah. Awesome. So that was with PNO. You can also do inverse problems, right? So I didn't, I guess one nice thing about these neural operators is you can directly estimate the inverse. Because these are differentiable, you don't have to do Markov chain Monte Carlo or other methods such as in numerical solvers, because most numerical solvers are not differentiable. So if you want to do an inverse problem, you have to do MCMC or other methods, which is further very expensive. So that's one good thing. But what we show is by adding the PD constraints, you can also make the inverse problem better behaved. So this example here, this is the ground truth input, this is the output. So what the inverse problem means is I'll give you the output, you have to recover the input. And so what you see here is if I only use data and I don't have any PD information, any physics information, my recovery isn't that good, right? So whereas if I incorporate the PD constraints and do the PNO framework, I can also get good inverse problems, which is natural. I mean, these physics helps you extrapolate, right? We saw the distributional shift. It also helps you do the inversion, which in general can be ill-posed or challenging. So that also helps you get to the desired solutions better. So I'll show you quickly some outcomes from using Fourier neural operator and in some instances PNO, but mostly most of our work has been so far data-driven, but it's natural to also add physics constraints and see how that would further make this better. So as a first example, what I'll show you is for weather forecasting systems. So here you see the atmospheric rivers, the prediction of this, which is thousands of kilometers wide. And this has a huge impact on precipitation in the western coast of US. And the lack of it is a drought, right? Too much of it is a storm. And so what we can do is do these kind of predictions very accurately, but be about 45,000 times faster than current numerical weather models. And in our case, what we did is purely data-driven, right? So ultimately, we want to add the physics constraints too, but as a first step, what we're seeing is even without adding any physics constraints, using only all the historical weather data, we're able to get very good accuracy. In fact, like a week on challenging variables like precipitation and wind. Especially precipitation is very challenging. And I'm sure, here in Boston, right, today, there was prediction earlier of 50%, there was 20%. So precipitation is a hard variable, and we are able to do as well as the gold standard weather models, but be much faster. And so, you can see that would also result in a lower energy footprint because inference in these models is very fast. And you can also get better uncertainty calibration. Because this is so cheap now, you can run this entire weather model on a single GPU. You can afford to do even thousands of ensemble members, right? So you can slightly perturb the initial condition. see how your predictions change, come up with uncertainty measures. And especially for extreme weather events like hurricanes, you want uncertainties also, because that's what matters in terms of should we evacuate people, should we plan for landfall. And so those aspects we can do very well in this example. And also many other cases. So carbon capture and storage, right? This is what, right now we're just barely starting to do it. We would need to do this at a huge scale. So that means exploring which wells, which underground regions are well suited for pumping carbon dioxide, storing it in water, right? How does the carbon dioxide and water interact? How does it depend on the permeability of rocks? So what we're able to do is if you give the permeability map, so this is saying how permeable is that surface deep underground. And this information is available from seismic and many other sources, right? Geological surveys. So we can take those. And once you have this information, these are wells that are present deep underground. And then we can look at the ability to predict how will the gas saturate. So the carbon dioxide over a 30-year period, how will the plumes evolve? And along with that, sorry, I think I had another plot of the pressure as well, because you want this to be safe. You don't want earthquakes to happen as a result of pumping this underground, right? You also don't want the carbon dioxide to escape. It should be contained in the reservoir. And those aspects we can model very well. And so what we did was a multi-grid version of Fourier neural operator. So we can train separate models on the fine scale near the wells, and then a coarser scale grid for connecting the different wells, because you see different wells are also connected because, right, they're permeable. They still interact with one another. So this is extremely expensive for numerical solvers. So we are about 700 times faster than what the solvers are able to do. And we are able to do full 4-dimensional modeling. We can do this for adaptation to turbulence and ultimately very turbulent drone flights. And so we can now have real-time predictions of turbulence, which wasn't possible with standard CFD solvers. And so we are doing that by collecting, this is laser here, and so just directly collecting experimental data and being able to model the turbulence, right? So we can do that very effectively. And so we're doing this with water as a proof of concept, but ultimately we could just have the drones themselves be available to collect, because it's very hard to model turbulence on drones, right? Standard aircraft wings, there's extensive wind tunnel testing, including, I know Boeing has one here, but you can't afford to do that with drones. So if we can collect even like kind of simple sensor data and from that learn a flow-informed model and be very fast, this can be very effective. And we are doing that also with online learning, with reinforcement learning very effectively. We're testing that in our fan array system at Caltech. So there, what you're seeing is like where the wind is coming from is small fans, and you can program that and create all kinds of patterns of winds. So it allows for very good testing of drones and other flying objects effectively. So I know, I think I'm out of time, but very quickly, I'll just tell you one other thing, because I know like the conversation says today, we were talking about the need for better initialization. So, standard neural networks, you can do random initialization, but that requires careful selection of variants, right? So if you select the variants to be too high, it leads to gradient explosion. If it's too low, it leads to vanishing gradients. So what we proposed is this framework called zero initialization. So what you do is you can do identity initialization when the matrix is square, when the weight matrix is square. So meaning you go from a layer of the same width, like 2 layers have the same width, you can just initialize your weight matrix as identity. But the problem comes when the width changes. And what we propose is the Hadamard transform as a way to avoid degeneracy. Because if you don't do that, you're degenerate and you're rank limited. You don't have good learning. And so that's the main innovation here. By combining identity and Hadamard transforms, we can get very effective training. So it is, the accuracy is similar to random initialization, but the benefits are you don't need batch normalization. You have better generalization in many cases with incremental learning, and you have applicability to any architecture. So it's not architecture dependent. So I know that this may be something of interest in many cases, especially, for instance, in Bayesian neural networks. This random initialization itself can affect uncertainty quantification, right? So there's one other source of stochasticity we can avoid, and so you have better reproducibility and better control on what the neural network is doing. But yeah, I'll stop here.
Thanks. This is really interesting. So you were talking about using functional representations of like the actual like physical geometric space. Have you thought at all about like treating the hidden layers and sort of the extent in that direction as another thing you can treat functionally and getting some sort of like tunable expressivity out of that?
I mean, there are functional representations, right? Because we can, what we're doing is approximating linear integral operators through those Fourier blocks. So, and that's why we can end-to-end keep the functional representation.
Yeah, thanks.
Sorry, I didn't hear the first part.
You mentioned the equals 5 pure levels under HGD, but they learn blocks with blocks. That's really hard to control. The Fourier stopping is something force it to run only defined scales. It seems like with your framework, that should be more explicitly controllable. Is that possible to do that?
Yeah, precisely. That's what we are investigating with this incremental learning, right? So what we are saying is, intuitively, if you can progressively increase the difficulty of the problem with natural images and other cases, it's very hard to do that. But here we know about the scales and we can control the resolution, right? We could even control the difficulty in other ways because we know so much about physical processes. And so as you make the problem more difficult, can you also incrementally either expand the Fourier modes or expand more layers? So that way you can overcome the difficulty of optimization landscape. So the idea is all this is great if you have lots of data, right? Then you can learn, but we're in much more data limited regimes. So the examples I showed you in fluid dynamics or even CCS, right? It's hundreds or thousands of examples, not millions or billions. And ultimately that's why we're also adding these physics constraints because we don't have enough data. And the optimization landscapes are very difficult. They're non-smooth with all the derivative constraints. So we need more than standard, optimization works out of the box for standard neural network. I mean, that's not true, but here the difficulty is very much multiplied.
A great talk. May I ask a question about the optimization? So optimization issues indeed are very annoying. So
I agree.
So recently, me, myself, and also colleagues from TechMarks group are concerned about this issue and also did some study on it. But my question is, do you have any advice in terms of to improve the optimization? Like here you propose the zero initialization. Like my question, what kind of optimizers, say, would you suggest, or any other technical details that we hardly even know?
Yeah, that's a good question. I think one aspect that is not well studied is how do these different explicit regularizers interact? So in the incremental work that I showed, some of the details, what we are exploring is like even something as simple as weight decay, right? So if it's done with the wrong amount of regularization can completely interfere and mess up the learning. So with standard deep learning, many of these hyperparameters are well tuned and it's okay. But in so many of these new domains,
we don't know what the regimes are, and maybe there are too many parameters to, and especially if you think of the PNO setting, you have lots of hyperparameters, right? So because you have lots of constraints. So you now have the PDE constraint at every point in the domain that you use. And so we can do also like primal dual approaches, but right, these are all, this is a harder competitive optimization problem rather than a simple optimization. And so I think, yeah, once you have all these enormous number of constraints, optimization becomes very difficult. And so the more we understand how these constraints interfere with data, that's important, because again, if there's enough data, it doesn't matter. This works, right? So the question is, if you have very limited data and constraints that are very hard to satisfy, in that case, would progressive learning help? So if I progressively start with easier constraints and coarser resolution and gradually improve, then the hope is we can overcome that. But that's something we are investigating.
Thanks. We're also very interested.
Yeah. Awesome. Would love to learn more. Yeah.
Maybe you kind of answered my question already. If you have high resolution training data, is that always strictly better? Or is there like practical value in going from coarser to high resolution?
So what we saw in our experiments, because we have the highest resolution data to begin with, right? So one is it'll definitely speed up training, because if you do it the right way of going coarse to fine, you don't need to compute on the entire finer grid. So you train faster. But the other is also we're seeing better generalization, and that's still we are investigating, is that universally true or not? In a way, it's intuitive, and even the beginning of deep learning, people try to do it, right? But the thing is, the difficulty is, you kind of have to make it progressive in the right way. Otherwise, it interferes, and you're suddenly changing the loss landscape. It doesn't then it's kind of, it has to relearn all over, but I feel like there's better promise with physical processes, because we know the gradual increase in complexity. We know in many systems, in fact, there is scale separation. In that case, you can certainly kind of keep it modular and do it as a multi-scale system. So that's why I hope it'll be better here compared to in standard deep learning, where doing some kind of progressive learning isn't being that effective.
So if you start with a high resolution data, it has a harder time of figuring out the coarse things first, and then gradually get more. This happens in practice?
At least that's what we believe. Because we haven't pushed the limits of it. We see somewhat better generalization by doing it gradually, but we want to take this further and investigate.
Okay, thanks.
Yeah.
Are there any other questions?
I don't know if online people can ask questions, or it's easy to see that.
I think there was one question online. It might have been partly answered, but given different meshes as input, their spacing and the frequency domain changes. So how can we learn a single R matrix, discretized Fourier spectrum, and expect it to work for different input grids?
So we have another paper on this geometric FNO, you can look at the details there, but at a high level, Fourier transform can be done on any, it's continuous, right? And you can do discrete Fourier transform on different grids. But of course, it won't be a fast implementation like FFT. And so now the question is, if you want to keep the speed of FFT, so keep it n log n, but also work on any irregular grid, what we proposed is to learn a deformation from irregular grid to a regular grid and do the FNO layers on that. And this generalizes well because you can learn a good deformation mapping as well.
If there are no other questions, I actually had one. So in the slide where you were talking about propagating back to the initial conditions, so does that only handle one deterministic answer, or are you also able to handle potential degeneracies and get a posterior?
Yeah, so this by itself will give you one answer, right? Because it's just the gradient. So you could, for instance, do ensembling of certain ways, right? You can do on top of it. You could make this probabilistic, right? So you can also like kind of do Stein's method, for instance. So those are, we have like some other works investigating ways to get also the right uncertainty. Yeah.
If there are no other questions, thank you for such a great talk, and thank you to everyone for joining us over Zoom and in person.
Yeah. Thank you.